All right, thanks, Rich. As Rich said, I'm Amelia Snyder, and I'm going to be talking to you today about the Hydro-Terrestrial Earth Systems Testbed project, also known as HyTEST. This is a project being led out of the US Geologic Survey's Water Mission Area, and the overall aim of the project is to modernize our hydrologic modeling workflows. So we're doing this modernization by trying to build an end-to-end open source scalable modeling framework that can support both our research modelers as well as our operational modeling efforts. And this is a multi-year project that has over 30 staff members contributing to it. I'm leading the computational environment task within this project. Roland Viget is our overall project lead. And I'm taking over the computational task lead position from Rich, who's been leading it for the past, I think, year and a half or 2 years about. And so I'm going to talk to you a little bit about our project today. So first, I want to cover just what are we talking about when we talk about a hydrologic modeling framework. And we sort of break our modeling framework down into 5 components. So the first one is this data management component. Our modelers need data. They have to have climate forcing data, geospatial data, so on and so forth. It needs to be stored in appropriate locations so that they can access it from different computing environments. It needs to be stored in the right formats to run their models. So we have an element that's focused on that piece of data management. We have a task focused on the computational environment. So where are our modelers running these models? Is it on our on-prem HPCs? Is it in the cloud, on their local computers? We want to make sure that we have the infrastructure for the modelers working in different locations to be able to run the models in these various places. We have a task focused on workflows. This is when you get into the data processing and analysis, when you're calibrating your model, how are you actually pulling in the data and the tools together into a workflow that can be reproduced to run this model? And then once we've actually run the model, how do we know if we did a good job with this model? How does it compare to other models? How does it compare to observational data? And this is covered by our evaluation task, which is really focused on the evaluation of model results. And then, that's all well and good if we build all this out for us to run it, but it's not much use if no one else knows how to use it. So we have a training task that's focused on teaching people how to use all of those components. And this training task runs both internal trainings within USGS to train people on these components, but it is also focused on building out documentation that's publicly accessible so that anyone, anywhere could reproduce the framework that we're setting up. So I'm going to dive into each of these components a little more just to talk about exactly how we're implementing these. Oh, actually, before I do that, there's some founding principles I think that sort of get at the core of what we're trying to build. So we're starting with a foundation of sort of standardized data that's in a cloud optimized format with direct access. So that's something like S3. Once we have the data stored there, we want to build data catalogs that can integrate with our external community systems. We want to use community adopted standards, tools, and approaches in our workflows as much as possible. We don't want to build our own tools and approaches. All of these workflows need to be scalable. So we have modelers working at really local scales that need to subset to just a small selection of a geographic region, all the way up to people running, the whole models over the whole US, and they need parallelized access to have efficient workflows. And we also want everything to be reproducible and accessible, so that not just people within the US Geologic Survey can run these. We want anyone, anywhere with cloud credits or funds to be able to run these models as well. Okay, so now I'll get into the components. So the first one is the data delivery piece. So at USGS, we have a requirement that we publish all of our data on a trusted digital repository. You don't need to worry about the details of that, but essentially it's a place that we publish data that is going to guarantee the long-term storage and maintenance of that data at a low cost. So this is a requirement of our agency that we publish this data in this location so that it's always available to users. But these long-term low-cost storage mechanisms aren't always performant enough for our modelers to do the work, or I'll say they're usually not performant enough for our modelers to do the actual work. And they also generally require you to download your own copy of the data onto the system that you're working on. So we're doing sort of a dual publishing mechanism where we do this publishing on the long-term digital repository where it will last sort of in perpetuity, but we're also providing an operational access layer. And this is where we store a more performant cloud optimized version of that data set that's available, while people are really actively using the data, but won't necessarily be around forever in the way that the published trusted digital repository data will be. So the operational performant copy of the data is what we're most focused on. Once we've published it in this trusted digital repository, how do we make sure that it can actually be used by the modelers running their models? And our pathway for doing this is, we start with where are we putting it? And we have purchased 2 open storage network pods. Each of these pods has a terabyte of data storage, and it's providing object storage with an S3 API interface. So we've got 2 of these pods stored at the Massachusetts Green High Performance Computing Center, which is on a high-speed internet connection. And after we've purchased these pods, now the storage is free and the egress fees are also free. There are no egress fees. And we find this to be a really important component for the storage and dissemination of these big data sets, because it's hard to predict how much those egress fees are going to be when you start to get into terabytes or petabytes of data. You don't know if a user is going to try to download the whole data set. So it's a risk to the data owner to take on that risk of paying the egress fees, or if you put the egress fees on the user as a requester pays bucket, that sort of inhibits access. Some people might not have the funds to access it, or they might be working in different cloud regions. And so that's a barrier that we don't really want to put up, to tell our users that they have to pay these egress fees every time they want to access our data. So we found the open storage network pods to be a really great solution to this, since we purchase them up front and then we don't have to worry about these egress fees, and we can store really large data sets on them. And so we're taking our model output, we're essentially turning them into cloud optimized formats. We're using ZAR most often, but we're also using file formats like Parquet, or maybe a collection of netcdfs with a Kerchunk reference JSON on top of that. And then once we've we've created our ZAR, we put it on the open storage network pod, we're cataloging it currently with an intake catalog. And actually this fiscal year, we're probably going to be transitioning that into a stack catalog. And so we have, over the past fiscal year, demonstrated that this is a useful way to publish data at USGS through the publication of our CONUS 404 data set, which was a 1 petabyte climate data set that we produced within the project. We stored it on a tape drive system to meet our requirements for this trusted digital repository component. And then we took the most useful subset of that model output, converted it into a ZAR, put it on our open storage network pod, and cataloged it with our intake catalog. And that is by far the primary mechanism that people are using to access that data set. And it's been quite effective for us so far. In terms of computing environments, we're trying to support people who are working on their local computers, people who are working on HPCs, and also people who are working in the cloud. So at USGS, we already kind of have our HPC infrastructure set up. Our modelers can run these, HPC workflows. They know how to launch Jupyter hubs in that environment. So our project has really been more focused on the cloud side of things. And we're interested in the cloud for a few reasons. I think the first one is that when these HPCs get backed up and we have deadlines to meet, we need somewhere that we can overflow and run these models and make sure we're meeting our deadlines, for one. Number 2 is we want anyone to be able to reproduce our work. And so by demonstrating how we run our models and run our workflows in the cloud, we know that others can reproduce the work that we've done. So we're trying to create demonstrations of that. And the third reason is we're interested in learning more about how much different modeling efforts actually cost, so that we can understand the true cost of the science questions that we're asking and better evaluate which efforts we should be pursuing based on how much the computing would actually cost to answer that question. So we're trying to learn a little bit more about all of those components. So the computing environments that we're actually going to build out in the cloud there's 2 of them. And the first one is AWS Parallel Cluster. This is meant to be, a mirror to our on-premises HPCs, so that people can easily transition between our HPC systems and Parallel Cluster And we're hoping to set it up in a way that doesn't require the modelers to refactor their code. They can kind of move seamlessly between these two environments. So we're going to deploy that. And then we also wanted to deploy a scalable analysis and visualization platform. And for that, we've chosen to go pursue Nabari. And Nabari is just a Jupyter hub with a Kubernetes cluster and a Dask gateway. And this allows our users to run Jupyter notebooks and alternate between, small computational lines of code and large parallelized computations without having to think very much about how they procure those compute resources or how they're going to parallelize their code. Dask and Kubernetes kind of do all this work for you in the background. And while we're talking about the computing environments, I just wanted to take a minute to acknowledge the Earth Science Information Partners Group, ESIP. We've had a great partnership with them so far. The USGS cloud environment is complex. We have a lot of user permission restrictions, security, networking requirements that are all barriers to us actually implementing, the types of computing systems that we want to use. And so it's a large investment for us in the government to try and deploy one of these systems just to find out if we're interested in using it. And so we've been partnering with the ESIP group to use their unfettered cloud environment to test out these deployments, see if they're actually useful to us, put some of our users in the environment, gather feedback. And then once we decide that a technology is actually worth pursuing, then we can go through the barriers of figuring out how to deploy it in our own cloud account. So they've been quite fundamental in us doing the work that we've done and choosing the technologies that we want to pursue. Okay, on the workflows piece, this is our data processing, analysis, visualization. This is really us just building out workflows that use the Pangeo stack just in the hydrologic modeling framework. So we're taking the data sets that the hydrologic modelers need, we're doing the types of analyses that they might want to do or the types of pre-processing for their models, and we're just demonstrating how to put all the pieces together. So we have some sample workflows that show users how to use X-ray to read in your data, how to use Dask to do parallel computations. We use some domain-specific packages like HiRiver and NetPy. We demonstrate using the visualization capabilities of HVplot. And then that's typically all shared out either in a Jupyter notebook for people who want to see the code, or we've been dabbling a little bit with the panel apps. And those are really great for people who don't want to see the whole notebook and all the code. And maybe they just want to explore a data set without having to worry about setting up, a Python environment or something like that. And so panel has been really great for that. So, this is us just sort of packaging this Pangeo stack in a way that's palatable for the hydrologic modelers on this component. And then the last component that I'll cover is our model evaluation piece. So we have a whole team that's focused on model evaluation. And this team does research on the types of metrics or analyses that we want to do to actually evaluate a hydrologic model output to determine how it compares to other applications. And so they sort of do the research side of things. And as they reach consensus around the best approaches or metrics to use, then they sort of build it into one of these Pangeo workflows. So they use the Pangeo stack to actually implement that mechanism. And the tools like Dask are really critical to this because we're often trying to do this analysis over many, many grid cells or many gauge locations within the US. So we've got some metrics that have been developed that we are promoting for the evaluation of hydrologic models. We have them documented and some demonstrations of how to use them as well. And also this is sort of a shout out or question. We're interested in publishing these metrics somewhere and we're looking for more open source Python packages out there that might be appropriate to build them into. So if anyone has any ideas on that component, please send them our way. And the last bit I'll cover is how we share our work. So we've built out a JupyterBook in a similar setup to what Project Pythia has done. And this is where we sort of bring everything together. And this is the main point for people to come and learn about what we're doing and what we're promoting. So we have chapters in our JupyterBook related to the computing environment setup and how to access it, how to access our data catalogs, how to read it into your workflow, how to do this basic geospatial data processing that the modelers might need to do. We have a chapter on model evaluation. What are the metrics we're using and how do you actually implement them on a streamflow model? So I would encourage you, I've got the link in here to come check out our JupyterBook. We have a good base of content in here, and we have a lot more content that's going to be coming this year. So it's very regularly updated. So keep checking back. And then the other space I wanted to promote is our discussion board. And this is a bit of a newer space for us. But we've set up some threads to discuss, the topics around data analysis in the hydrologic domain and model evaluation. And we're trying to encourage, rather than having these conversations internally just within USGS staff, we're trying to have these conversations out in the open and bring in people from other groups to discuss with us. So we've built out this discussion board and we're encouraging people to reach out to us through this mechanism. I've put this link in here as well too. We'd love to hear from you if you want to talk. And then I'll just end maybe on our future plans. So what do we have coming up this year? We're going to be building out some more cloud optimized versions of high value data sets. We have some more climate forcing data sets, some future climate projections coming out. We will be building out some key hydrologic modeling applications. We'll be building out ARCO versions of those data sets, and also maybe some observational data that is really key in the hydrologic domain so that we can evaluate our models against those data sets. We've tested out Parallel Cluster and Nabari in the ESIP cloud environment, and now we're working on deploying it within the USGS cloud and documenting that process so that maybe others who are working in more restricted cloud environments can follow that template. And then once we have them deployed, we're going to demonstrate how to run some key hydrologic models. So we're really interested in WRF Hydro, WRF, and NHM PRMS model. And we'll demonstrate how to run all of those models on Parallel Cluster this year. We'll continue as we start to run these models in the cloud. We can continue to promote this idea of scientific computing as a commodity, so we can see how much these various modeling runs cost and start to estimate what larger runs would cost and start to make decisions around which modeling runs we want to actually pursue based on their cost. We're also planning on building out a panel app for hydrologic model evaluation. And kind of curious if anyone in this group has any experience with building out really complex panel apps where you can map a model output, compare it to others, click on a point and create time series. We're a little bit curious what the performance of the panel apps will be like for such a large model application. So we'll be building that out this year, hopefully. And then the last component is we're going to be building out a Project Pythia cookbook that shows how we're using the Pangeo stack to evaluate hydrologic models. So that should be in the works for this year as well. And on that, I'll end this talk, Rich, and I'll hand it over to you, see if there's any questions.
All right.